Good morning. So today we're going to talk about, sorry, just give me a moment. Okay, so today we are going to talk about geoid and datum. Okay, we have already covered sphere, spheroid, and ellipsoid in our previous class or previous lecture. So the first topic of today is geoid. So what's a geoid? So geoid, many would say that it's nothing but a global mean sea level. So sometimes it's also known as MSL. It might, someone could define it in this way, saying that it's GMSL. All right. So this mean sea level is intended to measure the precise surface elevations and how it used to be used in the history in past days. So back in the day, people used to go to the sea or ocean with the boat, and they used to measure the heights of the the tides and the sea, the surface of the sea at different times, and then they calculated, for example, now this is the surface of the sea, this is the next surface of the sea, then we have multiple surfaces of the sea, and among them, based on all the calculations at the multiple points of the sea surface, they identified that, okay, this is the mean sea level. All right, so that means we can conclude that this line, this purple line, represents in some way all the variations of the sea level. So since this is the main value of the multiple calculations, that means calculations at this point, at this point, for example, if we have 3 points, three different locations, and then we have the mean value located at this point, mean value located at this point, and the other point. Okay, so now what we can do is we can simply connect these dots and have a line which contains the mean value of all the variations of the sea levels. So now it started giving us some problems. What sort of problems? When we come to the land, there is no sea. And since there is no sea, now there is no variation. I mean, the variation in the sea happens in a day. You could have multiple variations, but on land, you have to wait for years, couple of years, to see any variation on the surface. It could be because of the erosion and so on and so on. So as long as there were ocean or sea, it was fine. But then when you come to the surface of the land or surface covered by land, we stuck to a problem. So to solve that problem, now the scientists or the geographers, they proposed another idea. Okay, so how about we imagine a line which is perpendicular to the direction of gravity. So for example, this is ocean and this one becomes land. And in this land now, you could identify that the direction of gravity is in this way or this way. So now you can draw a line which is perpendicular to it. Okay, so you have multiple lines of or directions of gravity, and now thus you can identify a line which is perpendicular to the direction of the gravity. Okay, so it's also influenced by the density of the crust and mantle, etc., as well as the mass on the surface. Because if you go to Bay of Bengal, the mass, it's not that much, but if you go to Himalayas, then the mass would be significantly higher than Bay of Bengal. And if you go to the different continents compared to the oceans, then you will find the mass is significantly higher because it's containing the land, and land is comprised of different minerals and so on. So that's why if you look on the right, the GeoID, you will find the ocean is a little bit depressed, whereas different continents are elevated. And this is how actually GeoID look like. And this GeoID is taken from an animation of 2008. All right, so this is the GeoID height of 2008. So now you see that this GeoID is not regular. I mean, it is not spherical exactly like we have seen in the previous lecture, that we think of the Earth as spherical, it's sphere, and then we have GeoID, we have the actual surfaces, actual locations. So we find that GeoID actually sits between the actual surface, the actual terrain or the topography, and the spherical. It tries to mimic the spherical as much as possible by considering also the added and the reduced mass located on the actual surface of Earth. At the same time, it's tried to be perpendicular to the direction of gravity, so that the surface of GeoID is much smoother than the actual surface found in the topography. So however, for some practical applications, we find that a spheroid is a good approximation to GeoID, because of course, as I said earlier, we need that skeleton to find anything. So now if we try to identify how the mean sea level and GeoID differs from each other, and in these days, when people talk about, or when people say mean sea level, they actually mean GeoID. All right. That is a point to note. When people sometimes they would say that this is based on the mean sea level, the height is, the height is from the mean sea level, but the height is actually from GeoID, not from the mean sea level. Right. So these are the intersection points, A, B, C, and D, and this is how they are differing from each other. Okay, so GeoID is not always, below the surface of Earth. Sometimes, when I mean the surface of Earth, I don't mean is covered by land, but as I also mean that the surface covered by water, that's the ocean. So sometimes you will find that GeoID is even elevated or protruding than the surface of Earth. That means the surface of ocean. Okay, how could it happen? It could happen sometimes if you have some mountains at the seabed. So if you have some mountains at the seabed which is close to the ocean surface, then these mountains will be adding some mass at this point. Since the mass is added, the surface would be thus protruding or elevated compared to the ocean, and that's why you will find that GeoID is higher than mean sea level, or GeoID is even higher than the ocean at this point. So at the same time, if we also look at the line of the mean sea level, we will find that mean sea level is much smoother than GeoID. Why? Because mean sea level does not include the formation or the topography of the seabed. Rather, it only includes how the ocean is moving up and down. All right. So if we think about the ocean or the sea, the surface is quite flat. But if we think about the seabed, what's beneath this ocean, the surface is not that flat. Since the surface is not that flat, the gravity changes, or the point of gravity, it shifts, or it changes from point A to point B to point C. It changes with the location. All right, it changes quite rapidly, and that's why GeoID seems more irregular than mean sea level. And if you move from sea to the land, you will find that, okay, so at the land, the shape of the GeoID is even much more irregular compared to the, look at these points. Look at these points and this much, the ocean. Okay, this is very regular, whereas the land one is very much irregular compared if we compare these two. Okay, but if we look into the mean sea level, the imaginary mean sea level, that is for the land, or the calculated or approximate mean sea level or estimated, we find that it follows still the same smooth pattern. Okay, because if you have some curve like this, and if you try to estimate what would be the curve at this location based on these curves, you will still find something which are smooth. So point A and point B, this is land, and this is sea. Okay, so sea is smooth, and based on this data, when you try to approximate the data on the land, you will find that it's going to be smooth. So that's why the sea level is quite smooth. Mean sea level is quite smooth here, estimated mean sea level, whereas GeoID is quite rugged. It became even, it went frenzy at this between these 2 points compared to these 2 points. Why? Because of this irregular terrain. The terrain is quite okay, smooth, and the ocean is adding the much smoother surface. But then when it comes here, it's going very rugged again. On the other hand, if you think about the surface of ellipsoid or spheroid, it's very, very simple because it's simply a geometric diagram or geometric pattern. So that's why it has very smooth surface. It has very limited shape. So now that we established what's GeoID, next we are going to talk about is datum. And from GeoID, I mean, so far what we have been discussing is we have been discussing the spherical measurements. That means the Earth is spherical. That means the Earth is round. However, the surface is not smooth. That's established. So now when we do that, what do we do? I mean, when we calculate, when we take the spherical measurements of Earth, that is, when we calculate the measurements from the center of Earth, what happens? So what happens is it represents the Earth accurately. However, it does not preserve any of these. Okay, it fails to preserve the length, angle, and area. Okay, why? Because I think I have given this example earlier. If this is the center of Earth, this is the Earth, and you have some 2 points on the surface of Earth, and you take the angular measurement and say that the difference between them is 30 degrees, simply 30 degrees. Okay, there are 30 degrees, 0 minutes, 0 seconds. Okay, but this calculation fails to calculate the size of the area that is created on this surface of Earth between these 2 points. Why? Because this area depends on the distance between this point and this point and this point and this point, as well as this surface does not represent what is the topography of these two of the area between these 2 points. How? If you have, this is the 30 degrees. Now the topography, if topography is flat, simply flat, the distance between these two would be different, and thus the area would be different. If it's something like this, elevated, then the distance between these 2 points would be different, thus the area would be changing. So length is affecting the area. If this is something depressed, still the length is changing and thus the area, and in the same way the angle between the different points and locations are also changing. So that's why we cannot preserve all these things all together when we do a spherical measurement. And the units that are used in the spherical measurements are the degrees, minutes, seconds, or decimal degrees, or simply degrees. Okay. So, and these spherical measurements, as well as all the projected measurements, all of them are tied to an ellipsoid or a sphere by a datum. So that leads to a next question: what's datum? The datum is a reference surface. And we have two sorts of datum. One is horizontal and another one is vertical. So horizontal datum, you will understand just a little bit later in the coming slides. The vertical datum, it depends. It's a tidal datum, so it depends on the tides. It depends on the sea levels. It depends on the gravity. It depends on the GeoID. So how the surface is changing, based on the changes on the surface, the vertical datum also changes. So right. So for doing a datum, what do we do is a geodetic datum defines an ellipsoid, an initial location, an initial azimuth, and the distance between GeoID and ellipsoid at the initial locations. Okay, so that's a very academic description. Now, if we look into the practical descriptions or the explanations, they would look like this. Okay, so simply, datum is such that you have, I mean, we imagine that Earth is spherical. Okay, so the sphere or the ellipsoid that we try to use to represent that spherical shape is actually the datum. Okay, so let me explain it in Bengali. একটু আগে আমরা কি বললাম, পৃথিবী হচ্ছে spherical বা ellipsoid. Okay, so এখন পৃথিবীকে আমি বারবার বলেছি এই ellipsoid বা spheroid, সেটাই হচ্ছে পৃথিবীর জন্য কঙ্কাল। Okay, it's giving the shape. So এই যে আমরা একটা spheroid বা ellipsoid কল্পনা করছি, একটা কঙ্কাল আমরা বেছে নিচ্ছি বা একটা ফ্রেমওয়ার্ক আমরা ধরে নিচ্ছি, সেটাই হচ্ছে datum. Okay, so আশা করি datum জিনিসটা বুঝতে পেরেছো। So now the difference between simply imagining that the Earth is sphere and saying that now I have a datum, there is a basic difference. So what is the basic difference? I mean, if you think about Earth, you will say that, excuse me, you will say that there is only one sphere. I mean, if we have one Earth, so that means we have one sphere on one spheroid or one ellipsoid. That's it, right? But we could have multiple datums. How? We can move this spheroid or ellipsoid in different directions and identify for certain coordinate system, we could develop our own spheroid to represent that framework. And that's why we have multiple datums for different coordinate systems. Okay. So how is it? Let's look here. So this is the geocentric datum. I mean, this is the GeoID. The dark black line is the GeoID. Okay, the thick one. And for this GeoID, we have one spheroid, which is identified by these gray dots, dotted lines, or striped lines, we could say. So now this spheroid try to fit the GeoID as much as possible. Okay, and there are also different surfaces and so on. However, it fails to match the surface of GeoID at different points. For example, we have a large gap at this point. We also have large gap at this point. and so on and so on and so on. Okay, there are so many mismatches. So now, if we think about one coordinate system which is getting represented for the entire Earth or entire world, at that moment we consider the GeoID, and based on GeoID we try to match a spheroid with the GeoID as much as possible, and this one is known as geocentric datum. Okay, so geo, Earth, centric is the center. Okay, so it tries to match. I mean, the center of it is located at the center of Earth, and from center of Earth we try to draw one spheroid, and we try to match the GeoID as much as possible. And now, on the surface of this datum, we try to develop our coordinate system, our own coordinate system. For example, WGS 1984, which we have been talking about a lot. Now, for example, if we look into this and just imagine that this is USA, okay, this is USA, or yes, and we might find that this surface is not matching the, I mean, it's not matching the geocentric datum, and the GeoID has some mismatch at this point. Okay, so I'm going to clear this line so that you could see clearly. So these are the mismatches that we have. The gray line represents the GeoID, whereas the thick black line represents sorry, the gray one is the geocentric datum and the black thick one is the GeoID. So since this mismatch, and now, for example, my area of interest is only this region, only this much. Okay, so this is USA, for example. USA itself is a very large country. So this is my interest, region of interest. But then when I try to use WGS 84, I'm having some problem. Okay, what are the problems? The surface of the GeoID and the surface of the ellipsoid that I have for WGS 84 mismatches significantly. I mean, in this diagram, you might see that this gap is very little, but then think about this one is Earth is so huge. So this much gap is significant gap or significant mismatch. So now what can I do? Then the scientists or the geographers, they came up with a solution. They say that, okay, we are going to develop another datum for it, another datum for USA. And what do they mean by another datum? They actually mean they have developed another ellipsoid for USA. But this ellipsoid moves away from the center of Earth. Okay, it moves away from the center of Earth. Since it moves away from the center of Earth, I mean the center of this ellipsoid moves away from the center of Earth, then except this region of interest, at other points, this local datum or the spheroid that was created to match the surface of the GeoID at the region of interest does not match with the rest of the surface of Earth. So what are these regions? This is the thin dark line, thin black line is the local datum for USA. And if we look into the GeoID, it has significant large differences. See, at the other parts of the world, okay, it has very significant differences. However, it matches the surface of USA or the GeoID, which is located on the surface of USA or the region of USA. It matches to the, I mean, it have a very little difference. Okay, and based on that, now we could have a local coordinate system. Now this one is called local coordinate system for USA, only for USA. Okay, And these sorts of datum are known as local datum. So the characteristics of local datum is they are not geocentric. That means the center of their ellipsoid is not located at the center of Earth. It matches the region of interest. The surface of ellipsoid matches with the geoid of the region of interest. However, it moves away significantly, or it has significant mismatch at the rest of the world. So one quick example is NAD 83. It's very good for North America, but if you start to calculate or if you start to find locations of Europe or even Bangladesh, you will find that, I mean, you are moving away from the actual locations. So that means it will give you significant errors at the locations other than USA. Okay, so vertical datum, as I said earlier, it considers the elevation, the changes of the elevation. So now with that we have our datums ready, now we can have our coordinates built upon them. So for global datum, we have global coordinates. And for local datum, we have local coordinates. Okay. So I have already discussed the local and regional datum. So far we defined it as local datum. Sometimes they could be known as regional datum as well. Why? Because sometimes it could represent a region, for example, Australia. So Australia itself is continent, it's a region, or we could say USA or North America, that's also a region. At the same time, if we think about Indian subcontinent is highly dependent, and you will see today on the Everest 1830 datum. Okay, so this Everest 1830 datum is represents, or it's a datum developed for the surface of Indian subcontinent. And this is also very interesting because the surface of Indian subcontinent is gradually changed from south to north. So this is south and this is north, and you will find south is more depressed, going to the ocean. The north is going to the Himalayas. Okay, so it's a gradual change. Whereas if you look into the Australia, it's sort of going like that. So ocean on both sides, then it's elevating. Thus, you can easily match one spheroid in this way. Okay. Also, if we look into the USA, it's still same ocean on two sides, and then the land in between. So still, the Earth's surface could be matched by a sphere. On the other hand, since India's surface or the Indian subcontinent region is a little bit depressed on one side and elevated on the other side, and it's not in between oceans, so for matching, our geoid moves significantly away from the center of Earth. Okay, there is a large shift. So if this is the spheroid of Earth, it would be moving away on this, the center would be moving away on the northern side, okay, to match this surface. Anyway, so there are many regional datum. There are many local datum to satisfy the needs at some that respective regions. Okay, and here is the explanation. Because the Earth is so misshapen, the shape of Earth is really different from, or the shape changes from place to place. Okay, so if we look into the examples of Australia, you will find, or examples of southern hemisphere, you will find that when we try to draw a spheroid which matches the surface of the Australia or southern region, you will find that it significantly mismatches for the northern hemisphere. So there is also another reason, is the northern hemisphere has, I mean, most of the land areas or the landmass is located on the northern hemisphere. So it's more rugged terrain. And on the south is much of the terrain is ocean or covered by ocean. So when you try to match these terrains, and they are also less mountainous, except if you're talking about Latin America. If you go to Australia, it's less mountainous, except the New Zealand, of course. So when we try to match this region, we start to have the differences between the GeoID in the northern hemisphere and our surface of the spheroid. That's the local datum. Okay, so for Australia, it has AGD 84, or simply AGD. It was created in 1984. So that's why they have it. It has the best placed latitude and longitude for Australia, but then if you try to use it in North America or in Bangladesh, you will start having problems. The geocentric datums, they are located at the center of the Earth's mass. Okay, so it's coincides with the center of ellipsoid. It tries to matches the GeoID as much as possible. We have already established that. Okay, and also it's on the, if we go out of the Earth and if we look back, it would match the line of the equator and the cross section of north and south. It's at the center of that. And much of the GPSs, they use global positioning, the global datum. Why? Because the GPSs are devised or created to take the measurements globally. So since they are designed to take the measurements globally, they always consider the global datum. Okay? So based on this global datum, they calculate their locations. But then, for example, you could say that if this is USA, there is a significant mismatch. If it's Australia, there is a significant mismatch. If it's Bangladesh, there is also significant mismatch. Okay, so how can we overcome these? We can easily overcome these by transforming the coordinate system from which uses global datum to a coordinate system which uses local datum. And when you do the transformation, the software automatically, I mean, what it does is it completes or it calculates all necessary calculations to change this spheroid to a local spheroid. Okay, so maybe this spheroid has the center is located here. So the center has moved away this much. Also, the axis has moved away, right? So the software automatically calculates these changes and it transforms the coordinate system to the local coordinate system, and thus we do not have really any problem. So more examples of how local datum differs from the global datum. Have a quick look at it. They're interesting, these photos. I have already discussed. I'm going to skip that. Okay, have a look into this. I'm going to skip this one as well. Let's focus on the projected coordinate system. So far that what we have discussed is we have discussed geographic coordinate system. So GCS, the geographic coordinate system, is a three-dimensional coordinate system, and it has few elements. So we say that GCS represents Earth as spherical or ellipsoidal. Okay, then we have found out that, okay, so GCS highly dependent on GeoID, and beneath this GeoID we have for specific GCS, a specific geographic coordinate system uses a specific spheroid or ellipsoid, and thus that spheroid or ellipsoid is known as datum. Okay, so these datums can be both local or regional and global. So local or regional datum matches certain region matches the surface for the certain region with the GeoID, and the global one try to fit the GeoID with the spherical surface. Okay, so this is what so far we have learned, and while doing so, we have also talked about central meridians and equators, and when they cross, it creates the origin point, and based on these origin points and the lines of center of Earth, now we have lat and long. Okay, so this is the entire geographic coordinate system. Now we are going to talk about projected coordinate system, another dimension. So what is a projected coordinate system? A projected coordinate system is simply a two-dimensional representation of these three-dimensional representation. So if you have a geographic coordinate system, which is a three-dimensional, and if you try to project it on a two-dimensional plane or surface, that's your projected coordinate system. I could give a very quick example using a tennis ball. All of us have played with tennis ball when we were younger, when we were playing cricket. So now dip this tennis ball into a bucket filled with water, or filled with dirty water, or filled with some colored waters, and then throw the tennis ball on a wall, and you will find that the wall has impression, a two-dimensional impression of certain surface of the tennis ball. Okay, if this is a tennis ball, this is a surface which got impacted on the wall, and it has left out its impression on the wall, the mark of the tennis ball on the wall. Okay, so this marked area, which actually represents the surface of this tennis ball, the tennis ball is 3D, of course, and this impression is two-dimensional. So this is the projected coordinate system. So the coordinate system which is used to represent the three-dimensional Earth as two-dimensional are known as projected coordinate system. Okay, so this is the everything which is here. So আমি যা বলেছি সবকিছুই এখন এখানে আছে. All right, so you can explain it in this simple format, or simple way, very easy way, or you can go with this academic language and explain it. Either way is fine. So the thing is, now we are throwing tennis ball on the wall, and we're saying that is it the only way to have the impression of the tennis ball, and thus is it the only way to have the impressions of the Earth, because Earth is also like a tennis ball, it's round. So the answer is no. Why? This is the example of the tennis ball that we have been giving. We are throwing a tennis ball on a flat surface, and thus it's having some impression. This area is getting impressed on the surface. But what if now we create a cone? I mean, we all had cone ice creams. So in the cone ice creams, we have this cone, and then the ice cream sellers, they take a scoop of ice cream and put it on the cone. So the scoop is round, right? And the cone is conical. এটা কি জানো তোমরা? আমি জানি না তোমরা খেয়েছো কিনা। তোমরা এই যে কোন আইসক্রিম স্কুলে থাকতে অনেক সময় আমাদের বাইরে আইসক্রিম ওয়ালা আসতো, কোন আইসক্রিম থাকতো, এভাবে কোন নিয়ে, ও সরি ওটা আইসক্রিম ওয়ালা না, বিভিন্ন দোকানে কোন নিয়ে এসে তারপর ওখানে স্কুপ অফ আইসক্রিম, স্কুপ এরকম নিয়ে গোল করে, আইসক্রিমের স্কুপ গোল হয়, গোল করে নিয়ে একটা বল বানিয়ে ওখানে দিয়ে দিত। So now if we take off that example, even if you could think of your hat on your birthday parties, so that's also conical. Okay, so when you put it on, you find that it's touching some surface of a head, not the entire surface. So that means it's creating an impress in this region. It's touching this region, so it's having the impress of this region. And finally, all these tennis balls, they are sold in a cylinder, right? You could have multiple tennis balls fitted in a cylinder. So if you take the cylinder and if you make it tighter than before, and you will find that the tennis ball is touching the region which are located on the equator on the side or the sideways, okay, by the cylinder. So that's why we have three different ways to take the impression of this three-dimensional object and transform it into a two-dimensional plane. So one is conical, plane, and cylindrical. And for our class, the cylindrical is the most interesting one. Okay, because based on the cylindrical measurement, UTM is devised, which is a global coordinate system and globally used. Okay, so and this UTM is also, or the cylindrical measurement is also known as Mercator. So that's why UTM is Universal Mercator, Universal Transverse Mercator, right? And why is it transverse? Because it's measured through the equator. So this is the equator, okay? So when we take the measurement along the equator, I mean, this cylinder is touching the center point, or where it touches, the center of the touched area is on the equator or along the equator, as known as transverse. So universal transverse Mercator. So have a quick look into this. I'm not going to explain it, rather I talk about the interesting stuff. So UTM is one of the most popular projected coordinate system at this moment. Okay. So it's getting used worldwide, and it has 60 zones, and each zone has 6 degrees within it. Okay, and each zone overlaps a little bit. Now, what are the 60 zones? So 60 zones, if you search or if you Google it, for example, the locations of UTM, you will find that, location of Bangladesh in UTM, you will find that Bangladesh is located at 45N and 46N. Okay, 45 and 46 north. And why north? Because UTM is also divided by this line of equator. So we have northern and southern. So north, for the northern hemisphere, it's getting represented by the word N. And for south, it has S. So it has different zones. Okay. So when we combine these zones together, we find the entire UTM system, but still, UTM is highly dependent on the zones because each zone is independent of the other zones. And what do I mean by independent of the other zones? Because each zone has their own false origin. Okay, so for example, we are talking about this zone. This is the zone. Okay, so this is, let's say, zone 45, and 45 has its false origin here, and true origin might be light somewhere. Okay, let's put it in a different way. Let's say that this is the CM, okay, central meridian. This is the central meridian. That is the origin point. So for example, this is the origin point, the true origin point. But then we have a zone which is covering this region that includes, I mean, the true origin point is included in that region. So when you have covered this origin, covered this region, now just like graph, in graph we have 0, 0 origin point, and now we can identify 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Okay, we can identify any point located on this plane. To enable that, in this system, a false origin point is devised. So this false origin point is not located at the true origin point. I mean, it's not located at the true origin point of neither that zone nor that entire coordinate system. Okay, so arbitrarily we select a point as false origin point, and based on this false origin point, now we can calculate 1, 2, 3, 4, 5, 6, something like that. Okay, we can start calculating our x values and y values. So that means when we start to think about the next zone on the right, okay, so this is our next zone on the right. So this next zone also have another false origin 0, 0 for that zone, and every calculation is made, or every calculation is done based on these false origin, not this false origin for this zone. If this is zone 1, this is zone 2. For zone 2, it has its own false origin, and zone 1 has its own false origin. As a result, this zone is independent of the calculation of this zone, right? Now, don't forget this is going to be very handy when you talk about Bangladesh. This idea, all right? So let's go back to the central idea of UTM. So UTM is good from 84° north to 80° south. Why is it only good till 84° north and 80° south? Because if we go beyond that, I mean, look at this diagram. If we start to squeeze this cylinder, we might have impression of this region, right? But then this region is not really possible to make any impression because this is equatorial calculation. This is not oblique. Okay, আমরা বাঁকাভাবে এটা নিচ্ছি না, ইকুয়েটর বরাবর নিচ্ছি. So since the shape of Earth starts to squeeze or starts to converge into the polar region, so thus this coordinate system fails to represent these regions properly. Okay, because if we try, of course we can try, but there will be lots and lots of error. Okay, I mean, these properties of the converged would have, or pole being, the area being, moving away from the surface of the cylinder, could have some added errors. So that leads us to the question, what is the error at this point, at this region, within this region, which we can calculate? The answer is only 1 meter. Okay, so we could have accuracy of 1 meter. Since the error is 1 meter, we could have accuracy of 1 meter. I mean, our calculations are very accurate in some ways, and also it has minimal aerial distortion at this point. As I said, using this diagram, very less distortion in this region, but high distortion in the polar regions. So that's why we have very small errors in our calculation, and these also made this coordinate system very, very popular. So there are also some other benefits. However, let's talk about a little bit more on the UTM. Okay, so each zone has a central meridian, though they're its own central meridian, not the central meridian which went through the Greenwich of UK. Okay, so 60 central meridians in UTM. The scale is constant on central meridian. So on the central meridian, the scale does not really change. Okay, so if this is the central meridian, the scale is not changing. And also one important thing that I forgot to tell you is that this is the northern southern hemisphere's scenario, right? So what if you are talking about the southern hemisphere, Latin America or Australia or New Zealand? What's going to happen then? So in southern region, we have, you see, it says grid north. So this is the grid north, right? This is the 87 degrees north. So in southern region, we have a false north. Since the intercoordinate system is divided into north and south by the equator, when you talk about the southern southern hemispheres regions or the zones, which does not touch the north, this point, okay, because it does not consider this zone, and thus it cannot touch, or it cannot have this north grid on it. So it creates a false north, just like false origin point. It considers, or it creates a false north point or false north grid. Okay, and from this false north, it starts to calculate its calculations. So that's also yeah, it talks about here. So needs a false easting. So false easting is the false origin point, and false northing in the southern hemisphere. So this is the false northing that I was talking about. So UTM, why UTM? Because it has a good accuracy. The accuracy is of 1 meter, and it's a global coordinate system. And throughout the world, if you go from one place to another place, almost most of them, they know UTM. From UTM, you can transform your coordinate system into any local coordinate system of some sort. Okay, so if you have some data, if you are working in Bangladesh, and if you are familiar with UTM, and if you go to USA, you will still be deal with the data with UTM. If you go to Australia, or if you go to Colombia, by Colombia I mean, no, not Colombia, sorry. Colombia is a country, isn't it? Yes, Colombia is a country. If you go to Colombia in Latin America, or if you go to Brazil, you will still be able to use UTM. That means you will still be able to use a coordinate system which is familiar to you. And this is what made UTM very popular. So now in Bangladesh, we have a significant problem. The problem is the zones of UTM. In Bangladesh, we have 2 zones. Okay, so we have zone 45 and zone 46. So, and how is it a problem? Let's go back to the previous theory. We have one zone, this is 45, and we have another zone, so they have a little bit of overlap. Better I draw these in a different color. So we have another zone. So this is 46. Okay, so this is the overlap region. But the overlap region is not our concern. Our concern is this zone. These 46 zones origin point is here. For example, 0, 0. And the origin for the zone 45, we have origin point here, 0, 0. Now, if you have some study area, just like Bangladesh, which is located on both zones, if you identify in your software that, okay, my data is, because you can identify only one single zone in your software. I mean, if you open up your ArcGIS, and if you go to the listing of the UTM coordinate systems, it will give you the listing of zone 1 till zone 60. Okay, so you have to choose from this 1 to 60, and when you choose 45, you start having problem, because let's say this is the value of 1000 or 10,000. Okay, so this line ends at the 10,000 here, but then you have some data which are, and based on the design, it can have or it can represent a surface without any distortion within 0 to 10,000 point. Okay, and this 10,000 is here. And if we go beyond that, it cannot represent. It starts to have added distortion. That means it starts to add some errors. The accuracy is not 1 meter anymore. Okay, so accuracy is decreasing. Decreasing means lots of errors are being added. So if you start moving this way, you will have, when you stand on this point and start to take a GPS measurement, or if you want to make a special analysis in this, for example, this is Sylhet, you are doing a special analysis in Sylhet, then now you are having a problem. Okay, you are comparing the results of the Sylhet with Rajshahi. Now you are having a problem, because in Rajshahi, since you have identified this is 45 zone, it might not having any problem, but in 46 it's having lots of errors. Okay, similarly or conversely, if you identify the zone as 46 in your study area, so everything that's beyond this line is going to be negative, because they lies on the negative plane. Negative plane. So this is positive, we know, in the y perspective. So plus plus, plus minus, minus minus, minus plus. Okay, so if we are talking about this region in the western part, then they are going to be fall onto this part of the origin point. Okay, as a result, still error. So how to overcome that? Overcome this? So to overcome that, we have developed BTM. Okay, Bangladesh Transverse Mercator. And how did we do that? It's very simple. So we have two zones of UTM and Bangladesh in between. So we said, okay, how about if we combine these two zones and have our own origin point. All right, so the origin point of zone 45 is located here, for example, 00, and this is another 00 for 46. And then we scientists or the geographer in Bangladesh were thinking that what if we create our own zone, which is based on the BTM. We create our own zone by identifying our own false origin or false easting. Okay, and that's exactly what they did. So this was done in flood action plan. Okay, 19. So this plan was introduced in 1992. And in this plan, they used this BTM, they devised this BTM to represent the coordinate system of Bangladesh. So, and the central meridian for Bangladesh, they considered as 90° east. Okay, so this is the central meridian 90° east of BTM, whereas 45 has 80° east, sorry, 87° east, and 46 zone has 93° east. So you see, they took the middle point and created their own central meridian and created their separate false origin. So after the inception of these, it became very popular throughout the country, and now many websites, they follow this coordinate system. So you will find that BTM is largely dependent on UTM, okay? And that's why BTM, although it talks about it's only applicable to a I mean, it is a local coordinate system because it's only applicable in Bangladesh. If you go outside of Bangladesh, you are not going to be use it. Okay, if you go to even India, you will not be using it. However, it's a local coordinate system which is based on global datum. Now this is very interesting because local coordinate systems are usually based on local datum, but since I mean, this one is based on BTM, it uses the global datum WGS84. Okay, it uses the global datum WGS. This looks like something, so WGS84. So the datum is global, but the coordinate system is local, unlike other coordinate systems. So this is very interesting. Don't forget that. So now, how BTM is, how mismatch of coordinate system affects our representation. We have already seen it in ArcGIS to some extent, some data, but now here is one more example. And I think this is the last slide of today. So look, this is a road which is done in GCS WGS84. Okay, so this is the satellite image. The satellite image is taken using GCS WGS84. So we go through this. So this is the road. Okay, and there are also side roads and other things. And we find that there is a significant shift between the actual road in the reality and BTM, since the coordinate systems, two coordinate systems are different. Okay. Now what we do is we do the transformation. We convert, we transform this BTM, the data. So this is two different layers. At the background, we have satellite image. On the foreground, we have our vector road layers. We have shapefile. Okay. So what we can do is we can convert or we can transform. It's not convert for the coordinate systems, it's transform. So we can transform our BTM into GCS WGS84. If we do that, they will match. Okay, now if you look into this image, you will find that they are matching. Okay, the road is incidenting on the actual road on the satellite image. Conversely, what you can do is we can transform the GCS WGS84 to BTM. So আমরা BTM থেকে WGS84 এ কনভার্ট করতে পারি। So GCS WGS84 নরমালি এভাবে বলে না, সিম্পলি যদি বলে যে WGS 1984 বা WGS84 কোঅর্ডিনেট সিস্টেম, তাহলেই ধরে নিবা যে ওটা হচ্ছে GCS. So this is also another point. Never forget this throughout your life. If someone says my coordinate system is WGS 1984, okay, and don't argue saying that, oh, this is a datum, why are you saying that it's a coordinate system? What he or she actually means is that it's geographic coordinate system, because WGS84 datum was initially developed for the coordinate system, geographic coordinate system of WGS 1984. So they have the same name. All right. So datum and the coordinate system, they are under the same name. So jai hope. আমরা আমাদের রোড আছে BTM এ শেপ ফাইলটা। সো BTM লোকাল কোঅর্ডিনেট সিস্টেম যেটা, সেটাকে আমরা WGS84 কোঅর্ডিনেট সিস্টেমে 1984 কোঅর্ডিনেট সিস্টেমে ট্রান্সফর্ম করতে পারি। করলে এভাবে মিলে যাবে, রাস্তার উপরে রাস্তা চলে আসবে। অর আমরা আমাদের যে স্যাটেলাইট ইমেজটা আছে WGS 1984 কোঅর্ডিনেট সিস্টেমে, সেটাকে আমরা BTM এ ট্রান্সফর্ম করতে পারি। যদি BTM এ ট্রান্সফর্ম করি, তখন আবার রাস্তার সাথে রাস্তা মিলে যাবে। Okay, but if we do not do that, we are going to have some problems. And actually people, I mean, they are skirt. Oh, I have some other slides. There people are actually having problems. আমি তোমাদেরকে একটা স্ক্রিনশট শেয়ার দিব। Let me give me a second. আমি স্ক্রিনশটটা একটু করে বের করি। I should have it somewhere. Meanwhile, let me continue this. So, মিলে যাবে, right? So, what are the coordinate systems for Bangladesh? There are some other coordinate systems. One of them is Lambert conformal conic. Okay, so in these coordinate systems, you do not have to memorize or read all these things. I have highlighted few of them by making them bold to draw your attention on the datum of them. So they use Everest 1830, which is or the Everest Bangladesh datum. Okay, and the Everest is, for this datum they use the spheroid of Everest 1830. So this Everest 1830 or Everest adjusted 1937 is for Indian subcontinent. Okay, it was developed for Indian subcontinent, not only for Bangladesh. So this is a regional datum. Then we also use Indian zone grid, IIB. Okay, so the projection is still Lambert conic, and the datum is specifically Everest 1830. So if you want to know more about these coordinate systems, both local and global, they are usually they are usually cataloged here. epsg.io/3106. Okay, so even if you go to epsg.io and if you search Bangladesh Transverse Marketer or BTM, they will give you the result. All right, so at any point, so BTM is now, I think, now this is my personal opinion, I found that BTM, there are two versions of BTM available in Bangladesh. One is right, another one is wrong. So how can something be wrong? So something be wrong because when someone is dealing with the data or dealing with the coordinate system, sometimes they might not know what they're doing. So since they might not know what they're doing, sometimes they might go make something wrong. Okay, they might add some properties into it, or they might, for example, I can give you a very quick example. For example, you have a data which was collected using Lambert conformal conic. Okay, and now, I mean, the data was collected using this coordinate system. When you have the data, your data does not have any coordinate system. আমার কথা বুঝো, ডেটা ILCC কোঅর্ডিনেট সিস্টেমে কালেক্ট করা হয়েছে। এখন তুমি যখন তোমার কাছে যখন ডেটা আসছে, তখন ডেটায় কোনো কোঅর্ডিনেট সিস্টেম আইডেন্টিফাই করা নাই। ফর এক্সাম্পল, if you have already registered, I think I have told you to register in BARC, BARC. So if you download your data from BARC, their data does not have any coordinate system defined. Okay, so তাদের ডেটায় কোনো কোঅর্ডিনেট সিস্টেম নাই, সেটা ঠিক আছে, বাট তাদের ওয়েবসাইটে স্পেসিফিকলি বলা আছে যে আমাদের ডেটা GCS WGS 1984 এ ডেটাটা হচ্ছে দেওয়া। So that means when you will be working with this data, তোমাকে যে কাজটা করতে হবে, সবার আগে এটাকে WGS 84 এ ডিফাইন করে নিতে হবে। তো কথার কথা, এখন এই ডেটা আমি নিয়েছি, আমি তোমাকে দিয়েছি, তুমি আরেকজনকে দিয়েছো। এখন সে করেছে কি, সে জানে না এটা কোন কোঅর্ডিনেট সিস্টেমে, কারণ কোঅর্ডিনেট সিস্টেম তো ডিফাইন করে দেওয়া নাই, তোমাকে ডিফাইন করে নিতে হবে। সে মনে করলো কি, ও এটা তো BTM এ, তাইলে মনে হয় সে করলো কি, ডিফাইন করে দেওয়ার সময় সেইটাকে BTM এ ডিফাইন করে দিল। সো দ্যাট মিনস কি হয়ে গেল, তোমার কাছে যে ডেটা আছে, ফর এক্সাম্পল এটাকে সে করলো কি, এটাকে বললো এটা BTM নয়, এটা হচ্ছে WGS 1984। ওকে, তো এইটা সে যেহেতু একবার WGS 1984 এ সে ট্যাগ করে দিয়েছে, এখন ওই ডেটা ধরো পরবর্তীতে আবার আমি পেলাম বা যে কেউ আরেকজন পেলো, পাওয়ার পরে এখন মনে হবে ওইটা তো WGS 84 এ, কিন্তু অরিজিনাল WGS কিন্তু 84 এখানে, এই রাস্তা কিন্তু এখানে WGS 84 এ। তার মানে সিগনিফিক্যান্ট একটা শিফট, এবং সিগনিফিক্যান্ট মানে কতটুকু শিফট দেখো। ওকে, এটা যদি একটা রিভার হয়, রিভারের চাইতে বড় একটা শিফট। এখানে অনেকগুলো ঘরবাড়ি আছে, পুরো একটা এলাকা আছে, হ্যাঁ পুরো একটা এলাকা শিফট হয়ে যাচ্ছে, অনেকগুলো তোমার আমাদের প্যাডি ফিল্ড আছে। তো বড় একটা শিফট যখন এখানে অ্যাডেড এরর হয়ে গেল, এখন এখান থেকে প্রবলেমটা শুধু এখানেই থেমে নেই, প্রবলেমটা আরো আছে। সেটা হচ্ছে পরবর্তীতে আমি একটা ডেটা পেলাম, যে ডেটায় আমি জানি যে ডাটাটা WGS 84 এ কালেক্ট করা, এই এক্সাম্পলের কথা বলছি। আমি জানি যে ডেটাটা হচ্ছে WGS, ধরো এই ডেটা WGS 84 এ কালেক্ট করা, বাট আমার কাছে WGS 84টাকে আমি ওই জায়গায় অ্যাটাচ করে দিতে পারছি না। সো কথার কথা WGS 84টা হচ্ছে লোকাল কোঅর্ডিনেট সিস্টেম, আর GIS এ এটা ডিফাইন করে দেওয়া নেই, সেজন্য আমি অ্যাটাচ করতে পারছি না। তো তখন আমি কি করতে পারি, আমার কাছে অলরেডি একটা WGS 84 এর একটা ডেটা আছে কোঅর্ডিনেট সিস্টেম ওয়ালা। আমি করব কি, আমার ওই ডেটাকে আমি এই ডেটার সাথে কানেক্ট করাই দিব, কানেক্ট করে দিয়ে এই ডেটা থেকে WGS কোঅর্ডিনেট সিস্টেমটা আমি এখানে নিয়ে আসবো, ডিফাইন করে দিব। ওকে, সো ডিফাইন যখনই করে দিচ্ছি তখন কিন্তু এটা কিন্তু অলরেডি এরর, এটা অরিজিনালি ডেটা কালেক্ট করা হয়েছে BTM এ, কিন্তু আমি ভুলভাবে এখানে WGS 84 হিসেবে আইডেন্টিফাই করে দিচ্ছি। তো এই যে এরর, এই এররটা তখন এখানে অ্যাড হয়ে গেল। ওকে, কারণ তার যে প্যারামিটার, BTM এর প্যারামিটার ইজ সিগনিফিকেন্টলি ডিফারেন্ট দেন WGS 84, এই ভুল প্যারামিটার গুলো তখন এখানে চলে আসলো, এইভাবে আস্তে আস্তে জিনিসটা ছড়াই গেল। এটা একটা রিজন। আরেকটা হচ্ছে, we know that projection or the coordinate system is stored in .prj file. সো আমি এই ডেটা যখন বানিয়েছি WGS 84, তখন এখানেও কিন্তু একটা .prj ফাইল তৈরি হয়ে গিয়েছে। সো এখন এই কারো যদি লাগে, সে বলছে যে ভাই আমার কাছে তো 84 এর কোঅর্ডিনেট সিস্টেমের প্রজেকশনটা নাই বা ফাইলটা নাই, আমি ডিফাইন করতে পারছি না, আপনার কাছে কি আছে? আমি বললাম হ্যাঁ অবশ্যই আছে। আমি তাকে PRG ফাইলটা পাঠিয়ে দিলাম। ওকে, সো PRG ফাইলটা যখনই পাঠিয়ে দিলাম, 84 PRG ফাইল, সে এখন এটাকে ইউজ করছে, সে আরো 10 জনকে দিচ্ছে, 5 জনকে দিচ্ছে, পুরো ভুল একটা জিনিস প্রচার এবং প্রসার হয়ে গেল। ওকে, সো সিমিলারলি দেখো এখানে তুমি জাস্ট WGS 84 কে এখন এই জায়গায় BTM বসাই দাও, ওইটা হতে পারে LLC, অরিজিনালি ডেটা হয়তো কালেক্ট করা হয়েছে LLC, but someone has identified it as BTM, and now sometimes you will find that BTM এর যে ডাটম, এই ডাটমটা চেঞ্জ হয়ে যাচ্ছে। একটা BTM এ দেখবা যে এভারেজ 1830 দেওয়া, একটা BTM এ দেখবা যে এটা WGS 84 দেওয়া। সো ডাটম আমি সোফার 2 থেকে 3 ধরনের ডাটম দেখেছি আমাদের যে BTM যেগুলো সার্কুলেট হচ্ছে বাংলাদেশে। Okay, so that's a significant problem. কারো কোনো প্রশ্ন আছে কিনা? Anyone? যদি না থাকে, give me a moment, আমি একটু করে ওটা খুঁজে তোমাদেরকে দিচ্ছি। Interesting. ওকে, আমি ওটা এই মুহূর্তে পাচ্ছি না, কোথায় জানি আছে, আমি তোমাদের গ্রুপে শেয়ার করে দেবো। ইট ওয়াজ ভেরি ইন্টারেস্টিং। তো ওখানে যে জিনিসটা বলছে, একজন প্ল্যানার সে কমপ্লেইন করছে যে আমাদের দেশের লোকজন যারা GIS এক্সপার্ট প্রচুর প্রচুর আছে, সে ফাইল দিলে রং বেরঙের তারা ম্যাপ বানিয়ে দিতে পারে, বাট যখনই কোঅর্ডিনেট সিস্টেম বা প্রজেকশন আসবে তখন তারা কিছুই বুঝতে পারে না। তো তখন দেখা যাচ্ছে যে আমাদের একটা জিনিস আরেকটা জায়গায় চলে গিয়েছে। ওকে, সো ইটস আ প্রবলেম। ঠিক আছে, ওকে, থ্যাংক ইউ। কারো যদি না থাকে আমি ক্লোজ করে দিচ্ছি। Thank you.
Sir,